So hopefully none of you have the faintest idea of what I'm going to talk about. Okay? So we're all going to learn something tonight. Okay, so we're going to first talk a little bit about stars so that everybody's on the same page. No, I don't mean those stars, I mean real stars. So real stars are one of the roundest things you can find in the whole of the universe. I don't know why we keep drawing them as 5-pointed things, right? So first we're going to talk about the stellar daily challenges. So stars, they are constantly fighting against gravity, right? So gravity is this force that acts on things that have mass, and because a star has a lot of mass, it's very, very heavy, it tries to compress, the gravitational force tries to compress everything together in a very, very small volume, right? And if the star doesn't want to just collapse completely and become something like a black hole, it has to find some way of fighting back this gravitational force, right? And a star to do that, the star just makes up a little fire in its core. So it's almost as you had a bonfire there, but instead of burning wood, you're burning something else, in the case hydrogen, right? And you can imagine that this varies quite a lot depending on which type of star we are referring to. So you have this bonfire, it heats up the center, right? Because everything is very hot, it vibrates very quickly, and this creates a pressure, and this pressure is counteracting by gravity. So you can see if both forces are the same, then the star is not going to collapse anymore, it's going to be in a stable state, okay? And this varies for stars that are different masses. So we're going to have the help from Bob here. So the mass of the star is represented here by the books on the top of Bob's head. So if the star is not very massive, and you don't have many books on your head, then the force of gravity is not very strong. So if you have like a little fire on the center, if you're burning just a little bit of hydrogen, then you have already enough force to be counteracting this gravity. Now, as you increase in mass, the force of gravity gets stronger, and you have to exert an even stronger force to counteract the gravity. And finally, if Bob has really, really lots and lots and lots of books on top of his head, then he has to apply a lot of force. Now, to apply all this force, it means that you have to have a bigger fire, a huge bonfire. And it means that you're burning a lot of wood all the time, okay? So you're burning a lot of wood very, very quickly, so that you produce a lot of energy and a lot of heat so you can fight gravity, okay? So what happens if you run out of fuel, right? Because at some point you don't have an infinite amount of hydrogen to burn in the center of the star. You don't have an infinite amount of wood. So what happens when the fuel just ends? Well, then gravity wins, okay? And when gravity wins, everything starts doing what I said. It just starts collapsing because there's nothing to stop the gravitational collapse. And things compress a lot, and that thing, the star can become something like a black hole or a neutron star, which is a very dense object, and the surrounding gas around the star gets heated up a lot because you lose a lot of gravitational energy, and all this energy goes to heat. So what happens is you just have these huge explosions for massive stars, which we call supernova. So here we have a video from the European Space Station, and this star is going to go supernova now. And these explosions are absolutely amazing. The star releases so much energy in those explosions that at that point in time, the star can be brighter than a whole galaxy. Imagine a single star brighter than a galaxy that has millions and millions and millions of stars. Okay? So this is what we actually see. This is the Crab Nebula. In the center we have a very dense object that's a pulsar, and this is the remainder of a supernova explosion that went off. But the idea that I want you to understand here is that a light star, a star that doesn't have a lot of mass, burn less fuel because it doesn't need to oppose such a strong gravitational force. So it takes a long time until it actually runs out of fuel. So it's like this tiny little economy car, right? You can fill it up with a bit of petrol, and you can go a long way without worrying about refueling again, right? So they live longer because they can burn for a very, very long time because they burn very slowly. A massive star, on the other hand, is a bit more like a huge 4x4, like monster truck type of stuff. It's very heavy, and you put a little bit of fuel, and it consumes all the fuel very quickly, right? So these stars that are very big and very massive, they run out of fuel very fast, and therefore they die a lot quicker than the small mass stars, right? So this comes us to the end of the first bit. So the conclusions are that stars have to fight gravity every day. They burn fuel in their center to create heat, and the pressure from that heat opposes gravity. The stars that are heavier, they have to burn more fuel to survive, and if they burn fuel faster, they run out of fuel quicker, and they also die faster. Okay? Chapter 2. Right? Twinkle, twinkle, little star. So the stars, they shine, right? So we can think a little bit about how we see the light from the stars. So for that, we are going to use the help of Orion, which you might recognize here. And if you look with your naked eye on a clear night, so not like tonight, I can bet that if you look at Orion's shoulder, you can see a little red star here called Betelgeuse. And if you look at Orion's knee, you can see a bluish star called Rigel, right? So they have different colors, and that's related to also how hot they are. So who thinks that the hottest star is the red one, Betelgeuse? Can I have a show of hands? Nobody? A few people? Okay. Who thinks that the hottest one is Rigel? Okay, and I love that some people don't want to say anything. I'm not going to enter the situation. I don't want to look dumb. Okay, fine. So as it turns out, the blue star is hotter. So if you look, this is just the light, what we call the light spectrum. So light has something that we call frequency, right? Which is just how many times it oscillates as it travels in space, in a certain amount of space. So something that's very energetic or very hot wiggles a lot, right? And something that is not so hot wiggles less. So as you can see, the bluish light or the purplish light wiggles a lot faster than the red light. So in general, hotter objects are actually bluer, and colder objects are redder. Now you can see that this is just a very tiny bit of the spectrum, which is the bit that we actually see with our naked eye. This is the visible light. There's a whole lot of different types of light, which have either very, very, very energetic frequencies, which we can't see. So this is things like X-rays and gamma rays. And we have light that is so lazy that our eyes can't see them either. So those are infrared radiation, microwaves, and radio waves. And all this light is associated with the temperature of the body that's emitting it. So everything that has a temperature also emits light. So conclusion, you're shiny. You just don't know it, okay? So here, you see, as we see with our naked eye, but if you were able to put infrared goggles on, then you're going to find yourself in a bit of a spectrum here of things that are not so hot as stars, like ourselves, but still emit light at some frequency. So we are all here emitting in the infrared, right? If we were all to be animals that were able to see in the infrared, and some animals are able to see in the infrared, then this would be very bright, even in the dark. Okay. So, just making another point, Betelgeuse here is, so it's less massive. That's why it burns in the red. It doesn't need to oppose so much gravitational force, so it's not quite as hot. as Rygo, which is 20 times the mass of the sun. So that one is more massive, it has to fight gravity more, it has to burn hotter, okay? Now, there is something that I want to get across, that mass is not necessarily correlated to size. So, this is the sun. Can anybody spot the Earth? Okay.
Top left.
Yeah. So this is, you're here. Okay? So this is the Earth in comparison to the size of the sun. And you can see we are not very big. Now, this is the sun compared to Rigel. And this is the Rigel compared to Betelgeuse. So, yeah. So you think we're a speck of this speck. And then you know more or less the size that we are. Now, you can also see here the Rigel is a lot smaller than Betelgeuse, even though Rigel has a larger mass. Okay? So, Rigel is just a lot more what we call denser. It has more material per unit volume. If you were to put all the stars with the same density, so the same amount of particles in each box, then comparatively they would look like that, which is actually quite different. Anyway, okay, so conclusion slide number 2. So stars have different colors depending on their temperature. Blue stars are hot, and red stars are cold, right? We also emit light, but it's not visible to the human eye. And just because a star is big, it doesn't mean that it's the most massive, the one that has more mass, or the one that's heaviest. And we are really, really, really tiny. Okay? So chapter 3, tracking a star's light. So astronomers would like to know how stars evolve. So stars, like human beings, they are born in a certain way, they live a certain life, and they die in a certain way, right? And there are very good places to study the evolution of stars that are called clusters. So those are just a bunch of stars that all formed at the same time in the same place, okay? And there's something very important about clusters, and that's related to how bright the stars are. So imagine that I have a bunch of candles, right? And they are all identical, right? If I put one right close to your face and one on the other side of the room, which one is going to look brightest? The one closer to your face, right? Even though they have exactly the same what we call intrinsic brightness, they all shine the same amount of light, right? The one that's closer to you is going to look brighter. Now, when we are dealing with clusters, because they are all born at the same place, the one that looks brightest is also the one that's emitting more light, which is not often the case with other stars in the sky. Because sometimes you have really faint stars that are really close to you, so they look bright, or really, really bright stars that are very, very far away, so they look faint. So when you're looking at a globular cluster like this, then actually the stars that look shinier are actually the ones that are emitting more light. And that allows us to classify the stars better and allows us to track their lives better, okay? So what happens if we separate the stars by their color, which we saw that they are associated with the temperature of the star, and just their luminosity, how shiny they are? Then we get something like this, right? So the stars have different colors. This is the color temperature scale. And you can see a lot of stars are concentrated in this middle bit. This middle bit is called the main sequence. The main sequence is where every star is at the very start of their life. So that's when a star is born, it basically just appears somewhere here, depending on its mass. If it's really massive, then it's gonna fight gravity more strongly. It's gonna need to be hotter, it's gonna be blue. If it's less massive, then it's gonna need less heat to fight gravity, is gonna be in the red, okay? And once the stars run out of hydrogen first, then they start evolving out of this main sequence and they come towards this big other place, which is the giant branch. And then here they start burning anything that they can find really so that they can keep alive before they evolve to become either a black hole or a neutron star or a white dwarf. But the only thing I really want you to pay attention to is that you have this place where the stars are born, which is called the main sequence. It goes on a diagonal here, and once the stars runs out of hydrogen, it goes out of this main sequence, right? And it works pretty well. So here is another video which shows us trying to do exactly this separation by color and brightness for a certain globular cluster, which I showed before on Nina Sartorio. So here you have the globular cluster. So now what we are going to do is we are going to separate everything that's red on one side, everything that is blue on the other side. Okay? So now we separate them just by their color, and then we are going to separate them depending on how bright they are. And you see that we recover something that is sort of similar to what I've shown you before, right? You have this main sequence where all the stars are found, where those are the stars that are still burning hydrogen. Then you have the red giant branch, which is where the stars that are trying to burn other stuff. And then they slowly go to this blue branch before they, for example, start like the sun is going to become a white dwarf, which would be found all the way down here in the diagram. And that's why globular clusters are so helpful, because we can construct these diagrams very accurately. So conclusion slide number 3, the luminosity, how shiny the stars appear, depends on how much light they emit, but it also depends on how far away they are, okay? Clusters are a bunch of stars that have formed together at the same place at the same time. So the shiniest star is also the one that's emitting more light, okay? And we can organize the stars nicely on this sort of diagram that shows the evolution of stars over time, okay? So let's talk about the title of the talk, which is about blue stragglers and how they form. So the interesting thing about those globular clusters is that just by looking at the diagram made for each globular cluster, you can tell how long it has been since the cluster has formed. Okay. So the idea is all the stars are born in this main sequence, right? This diagonal on this diagram. Once the stars here, they are hotter and they are more massive, remember? So what happens with stars that are hotter and more massive? They burn more fuel quicker. They are the big 4x4 trucks, so they die faster. So as they start dying, they start evolving out of this diagonal, so they go to the side, right? So after 100 million years, all these more massive stars have already been able to evolve to something else. And if you wait even more time, then the medium mass stars start dying as well and evolving off. So just by seeing where this turn-off point is, we can basically say, ha, this globular cluster is this age, or has formed that long time ago. Okay, so let's see if you're paying attention and if you can understand. So if you have just a lot of stars that are lying this red line and this one, which one is oldest? The one with the heart or the one with the flower? Yes, the heart, because this one's already evolved out. Okay. Now, these two, the one with the plus or the one with the rainbow? The plus. Okay. Okay, final one. The one with the hourglass or the one with the boat? Hourglass. Okay, what about this one? What is happening here? Right? These ones evolved out, but these ones are still in the main sequence. What's happening? of the spectrum, right? They're emitting in the blue, so they're these big, massive stars with lots of mass. But they seem to be struggling behind in the evolution. They are kind of left behind. Everybody else went and evolved to a new life, and they are still there. No, I want to be in the main sequence, right? I want to continue burning hydrogen somehow. So we were like, what happened? So they shouldn't be there anymore. They shouldn't have any hydrogen left. Why do they live longer? What's their secret to remain young, right? Did they find the fountain of youth, right? And astronomers came with lots of different theories of why those stars were there, because we saw them in lots of different clusters. Are we understanding stellar evolution right? Right? Why do they evolve differently? Maybe if they rotate faster, they can burn a different amount of fuel, and it gives you incredibly complicated theories. So then after a little while we stopped and we thought, maybe they're not young. Maybe they just put some makeup on, right? So they are old, but they want to appear young. So I'll just paint my face blue, and then there, I'm blue. And so from what we just have been talking today, we have to think. If you want to become more blue, if you're blue, it's because you're hot, right? If you're really hot, it's because you're big and heavy and you're trying to fight gravity. And means that you're, yeah? So if you're trying to fight that much gravity, it must mean that you were a thin star at some point, and then somehow you gained weight, okay? So it's a little bit thinking about stellar dieting, and astronomers came with 3 different ways of trying to explain how a star can gain mass and therefore get bluer than they were, right? And appear younger. So we have 3 theories: the bully theory, the cannibal theory, and the vampire theory. Okay? So the bully is just, you have the star and it basically hits the other star, and they just join together and they form this bigger blue star. So because they were both smaller and redder earlier on, their mass together is actually pretty big, right? And then they can appear as being a blue star even though they weren't. So you join 2 smaller stars to get 1 bigger blue star. There is the cannibal theory, which is you have just 2 stars that are in a binary system, so it's 2 stars rotating one another, around one another, and then 1 star that's slightly more massive just starts stealing material from the other one until this one gets completely sucked in, and then it also becomes 1 big star. And then the other one is the vampire theory, right? And this one is just, you have the binary system like in the other one, but the one with more mass just starts sucking in a little bit of the mass at a time. It doesn't necessarily take all the mass from their companions, so you can end up with 2 stars, 1 bigger, more bright blue star, which is more massive, and 1 that is tinier, that is just going to evolve slightly different. And it turns out that we have been able to observe the vampire stars in terms of stellar dieting. So we actually see this really big evolved star. So when the star goes giant, so one of the stars goes giant, it becomes very big, and sometimes because it becomes very big, it starts getting in the way of another little star that's around. And this little star starts gathering material from this star. This big star evolves to something like the sun is going to evolve to a white dwarf, so you have a tiny white dwarf. And you can see the bright blue straggler. So we started seeing that a lot of the blue stragglers that we found were actually found paired up with a white dwarf. And it's exactly because you have this big, massive giant just feeding in material to this blue star, to this other star, which eventually becomes blue just because they gathered so much more mass. And this is the conclusion number 4, and I promise this is the last one. So blue stragglers are just, they're just stars that appear younger than they are. They are not necessarily, they're not really younger. They just masters of the skies. And they're stealthy thieves that get their mass from their companions, their partners, right? And because they increase in mass, they also start burning more fuel, which makes them hotter, and they're bluer and appear young. And that's it. I would say happy observing, but it doesn't sound like it's gonna happen tonight. So